Okay, right. Okay, well, welcome and thanks to all of you for coming along. I do appreciate the time that you got for this. So just a little bit of introduction to the IOP team. So I'm Andrew Bailey. I'm the dot in the kind of southeast area in Dundee. And these are the other IOP physics coaching team led by Stuart, who you've seen on the call already, and Jenny's also here as well. So we're here to support your professional development in terms of physics. Some of you will have signed up to the IOP emails. If you haven't done so, there's an opportunity to do so in the link from there. Most of you will be on the Sputnik email forum, the Google group as it is now. There are over 800 schools, well, 800 people on there from most of the schools in Scotland. So we're keen to share that and to reach out and find as many people as we can and support them to those. So if you're not on there, it's well worth signing up to as well. A little bit, the IOP have various processes and policy documents in terms of looking at inclusive teaching for different genders, ethnicity, and trying to make physics more inclusive. So if you're trying to do that within your school to improve the inclusion, then there are various reports that you could have a look at from our Limitless campaign. Quick plug for some forthcoming events. So there's one tomorrow on engineering science and one in December on Newton's laws of motion. So you can sign up for these on IOP Spark website, and the events part of that you'll get to see those. And then lastly, in terms of the events, this year coming up will be the 50th Stirling Physics Teachers Meeting at the Stirling Court Hotel just during study leave. And so we hope that you will be able to join us in person to do that. We're looking forward to an extra special event to celebrate the 50th year. You can find out details if you Google the event. You'll see where you can sign up and what to do, and details will be coming out ahead, but you can certainly place it all in the diaries for that. A couple of things on resources. You might be aware on the footer on the Sputnik email, there's a link to the Google Docs spreadsheet with links for various different parts of the course built on from the lockdown process and kind of evolving a little bit as we go forward. Okay, so we'll be going on to our meeting first. I will share with you the evaluation at the end as well, so you can evaluate and tell us what you think, because we're basically here to try and meet your needs, to try and help you with what you want out of it, but that is more useful if you inform us what kind of things you would like and what you're finding useful and what you're finding less useful, if you like. So onto the main event, if you like. What I've obviously got a slide up here looking through the abstract section of the report. So I was contacted, the reason for some of this session is I've spoken to a number of teachers who've wanted information about how to improve the marks that they're getting on the project reports and on the assignments. And I thought, I've done sessions before on sort of selecting the experiments and how to support a bit of that. And we did one last year, myself and Catherine Dunner-Cirque, on the actual projects. So we can link to some of that, but this one is a bit more about the writing of the report and how students are doing things. So it's based on the course reports that come out every year, and also based on using extracts from various documents to highlight some of the things that candidates can do, and by being more aware of those we can maybe help them avoid some of these issues, because at Advanced High you are allowed to give degree of feedback. You can't reword and rewrite the reports for them, but you are able to advise if there's things that are in need of improvement and how to do that type of thing. So if you like, what we'll be doing is going through the different sections of the reports, and we'll highlight some of the things that can happen and use some of the passages from student reports to kind of illustrate some of those problems. So I appreciate some of the text is quite small in the bodies and things like that. So I'll be sort of highlighting different things just to kind of point out things. Because I do some of the marking as an appointee. I've been fortunate to do that. So you do see projects from different centres, and then the information is fed back through the course report to centres, but sometimes there's things that you pick up when you see. And what's always unclear is whether that is the student not listening to the teacher, or whether it's the teacher maybe not being quite certain about what to do, or often a combination of all of those things from there. So we're going to start with the abstract. So the abstract, they're looking to present the aims and the findings from each procedure. And yes, you can have a copy of the PowerPoint later on, certainly to look through. What we'll be doing is looking that these things match up pretty much. So often you find that depending on what aim they write, the abstract and the conclusions don't quite match between the two. So if they are making a comment in this case, and this person's talked about the most accurate experiment, that's fine, but their aim needs to reflect that they wanted to determine the most accurate experiment. Or if they don't put the most accurate what part, then they just need to report the values that happen to be there. Okay, so any of those are possibilities. They just need to reflect the two things, and they'll still have a chance in the evaluation sections to talk about the accuracy and the precision anyway. So it's sometimes easier advice to keep the aim straightforward, and then the conclusion is straightforward, and you've still got the evaluation part to take place. So this one here, they've talked about getting a value for G, but then they've talked about it being more accurate than the other ones, and that wasn't actually in part of their aim that they had. Okay, if they're comparing, then they need to use the correct terms, so they do need to use accuracy or precision, and they need to be a bit more precise in terms of the language, because you often see people talking about method A was better than method B. What do they mean by that? So it's about trying to get the clarity for that. So sometimes it's a harder question if they want think about precision or accuracy to actually answer. Okay, so they might have a conclusion, and the conclusion might be stated on the fact that there's a relationship, and then they need to make sure that they're stating the right relationship. So if the best fit line doesn't go through the origin, they can't say it's directly proportional, because it isn't. Okay, it's proportional, but it's not directly proportional. So things that we know about, but advanced higher, they're expected to have these things commensurate and matching with each other. So sometimes making it simple makes it easier to do, to be honest. If they have the abstract, then they should you're looking for them to report on the values and the uncertainties from each experiment that they have. So they want a simple description of what they would need to do, and this person's done 3 things for the moment of inertia, but they've only reported a mean value. So I'd be expecting in the abstract to have experiment 1 and a little bit about what that was. Doesn't have to be very much, and then the result and the uncertainty rather than a mean. Okay, and we've got the same kind of thing. So acceleration due to gravity by conservation of energy on a slope, and then they've got a conclusion what it is, and then something about they've rounded it, and then this is higher than the expected value. So that's obviously an evaluative comment. So that would be better in the evaluation section rather than in the conclusion section, given that they weren't going to comment on how accurate it happened to be. Okay, so the aim or the aims should be explicit. You should include a brief procedure. So this person here on doing simple harmonic motion has said, I've used 3 separate methods, but they should have put what they've done. I've done a simple pendulum, I've done an oscillating spring, I've done ball oscillating on a mirror. So just a little bit. You don't want too much, but you want just a little bit to tell you what is taking place. Okay, doesn't need to be as detailed as the bit at the bottom there, but simple pendulum would be sufficient. Later on, they have to include things about the method and so forth. Okay, so a sort of general point, avoid averaging between the experiments that you've got. So they're determining the wavelength. In this case, they've done different experiments, and that's fine. Just report 656 and 685 and your uncertainties. You don't have to do an average between the two because they're not the same experiment. So it's an invalid approach. So it actually makes it worse that you're doing that. You just have to comment on what the results are when you're in the evaluation section. Okay, so that's the abstract section, and then we'll move on to the underlying physics part. And much like the assignments at all levels, it's about stating the relationships. Advanced high, it's about including the derivations, and it's trying to show understanding. So if you can make some commentary, or the pupil can make some commentary to show that it's not just a copy, much better. They should define the terms with the units, which is what's good practice at National 5 and higher as well. And in general, although they love putting things in, avoid history and non-physics information. It's interesting, perhaps, but it won't get any marks for it. And so potentially it could affect their word count in terms of them getting penalized if they use more than the 10% extra that they're allowed. Yeah, but sometimes your candidates don't take your advice. I had one last year exactly like that. He said, no, but it's interesting. I said, well, it is interesting, but it's not going to get you any more marks, and it's not particularly relevant to what you're doing. Okay, so here's an example of some derivation on the right. And there's a bit of commentary, if you like, about how it's taking place. So if you see a bit of commentary, then you're more inclined to think that they understand how it works out in terms of what they need to do a bit. And then there's some things defined, although they haven't defined the spring constant. Must be from a different experiment, but there's no unit for that one. But that's what I'd be looking for, defining all these terms that are on the right there in terms of how to understand it. So you're trying to say, well, there it is, and I can reference that, but equally I can explain where it's coming from. And of course, sometimes that's a challenge when they go into too much detail and it's too difficult to explain. So there is a balance between what you put in and it gaining marks because it's actually more understandable and better to comprehend. Okay, in terms of the procedures, the most recent sort of guidelines is that the principal examiner mentioned that we're advanced higher, they're looking for experiments, and it's usually 3, probably, depends on the time. We'll talk about that in a minute, but we're looking for different apparatus. So you wouldn't want all of the experiments to use the same apparatus. So this was from a picture on looking at moment of inertia and things like that, but equally there's similar one for sort of vibrating strings would have been a project done in the past. So they're trying to look for a different setup for some of them, so they're not all the same thing in terms of the approach that it happens to be. Okay, so different experiment is, so that's part of the recommendation in terms of how you're looking at what kind of approaches they're taking rather than doing the same thing. It's not the same thing because they're changing different variable, but it's seen a little bit as the same thing. Okay, so in terms of the selection, looking for an experiment that allows for graphical analysis. So in the past, it was accepted that there could be ones that were just numerical analysis, but it's really preferred to have graphical analysis. So that allows all the marks to be accessed. It's typically 3 or 4 experiments. They should be different to other candidates unless you've got a large center, in which case there could be some duplication of parts of the experiments between the things, but equally they should be done individually as well, so that so that there's no collusion, if you like, no copying of things. And there's 10 to 15 hours looking at time. Now that's a bit subjective because we all know have candidates and people in our classes who can spend a long time doing something that might take somebody else quite a short time to do as well. So it is a bit subjective. Okay, so that's a bit on the procedures. In terms of diagrams, that comes within it. So you're looking for information that has sufficient for the reader to replicate, or as I say, somebody else in your class to go and do your experiment. So we've got a nice picture here of somebody setting up a laser and diffraction grating and the different angles. However, this wouldn't be sufficient necessarily on its own to set up. So it's a good idea to take a picture and then they can label the picture as well. So you can have these sort of theoretical diagrams and you can have the actual diagram to show the setups, because sometimes that's the fiddly bit, how you hold the objects, how you do different things, those type of things. Okay, so here's another one of somebody reflecting off the ruler, and it's used as diffraction grating. Perfectly good experiment, but there might be some questions. If you gave that to your student, would they be able to set it up? So what's the screen look like? How's the laser held? Yes, it's probably in the clamp side, but if you send a picture, if you take a photo of it and try and avoid all the mess in the background, so try and make it kind of clearish to see, then that works out as well. Okay, sometimes images drawn on the computer. So this is one of maybe a Biflia pendulum, rod held by 2 bits of string. In essence, if you gave that to a student and said set it up like that, they might have difficulties because they're saying, well, how's it held up? So you want a picture of the clamp stands to show how it's held and how you're tying the strings at the top and how you're changing the length and things like that. Okay, so the diagram is fine to put in and part of your theory and part of the understanding, but it needs to be enough to make sure that you can replicate it. Okay, so somebody else here is using a Tiltron tube for an experiment. If you've got electrical things, you should include a circuit diagram. So include the one from the manufacturer's book, probably in this case, or a simple one, just showing how things are connected. Same if you're looking at inductors or resonance of capacitors or any electrical circuits. Stick one of those in as well as the diagram of the actual equipment per se itself. Okay, in terms of the actual procedures, we're looking at past tense passive voice. And if you have more than one slip, then you will lose a mark. They can only have that mark marked out of 1 instead of 2. So if they've got woulds rather than was and is, then obviously that's going to mean that the maximum for that bit is only 1 mark. And that's, of course, that they might be writing 3 procedures for 3 experiments, but they're still only going to get maximum 1 out of that. So that's something to flag up in terms of tense. Okay. Make sure the experiment is at the appropriate level. So we're looking for the time and we're looking for things that are commensurate to advanced higher level. So there's a picture of G by freefall. So we could probably argue that that isn't appropriate for high level. Sometimes things are included as a kind of initial thing, but then you'd need to make sure you extended it. So if you're doing a project on refractive index, you may well do a more typical Snell's law experiment and then treat it appropriately with sufficient repeats and uncertainty analysis, but you would need to make sure that your other methods are at advanced high level. It might be that you consider with your laser that maybe you want to do a double slit experiment rather than a diffraction grating experiment, just because the double slit theory is in the advanced high course compared to the diffraction grating being more at a higher level. It doesn't mean that you wouldn't do things to do with diffraction, but you might want to extend it to be like that. And we're trying to avoid, as we talked about before, things that use the same equipment with you just changing a variable. So the vibrating strings being a classic example where you might have changed the tension in the string, you might have changed the thickness or the mass per unit length of the string, and you might have changed some other variable, but it's kind of the same thing. So they're trying to look at things that are now different. So you could do a couple like that, but I would do at least one that was different. Okay, so moving on to the data section. Same as always, include units for everything. Okay, so here there's a missing unit for range. It's unusual probably to put the range, but they have put the range, but they should have put seconds next to that. Seem to be doing something on diffraction, lines per meter. Not sure we'd write it quite like that. So you can see these kind of issues that might arise from there. We've got somebody doing a pendulum experiment, and they've got 10 oscillations that look 11 seconds, and then they've got the time for one being 0.91. So something's not quite right there. And these are the kind of things, and all the other numbers look a bit like that. Now, obviously, it looks like they've done different number of oscillations for some of the different values that are there, but those type of things need to be clear. And this person here's put uncertainties within that part. What I would do is put them in a separate column rather than associated with the other parts. Okay, a little bit about incorrect averaging. We know students who would work out G by substituting into all the numbers into a formula, and they could then work out a value for G for each row of data, whereas what they should actually do is plot the graph and determine the gradient of the graph, and then use that value to determine the average. So they've done incorrect averaging. And this one's for G, but you could do similar things for some of the other experiments incorrectly. And I've often seen people who have done the graph and they've still got a value for each one. I'm like, no, take that out and do the next bits. It seems to be less common, but there's still a little bit of that does go on. Repeat all the data that you do. So this person was doing simple harmonic motion with a spring oscillating, or possibly G with a spring oscillating. And they measured the mass and the extension to find the spring constant, but they didn't repeat that experiment. So it wouldn't take them long to hang the other masses back on and measure the extension, but there was no repetition there. So it's a case where if you've got two things and maybe it's a little bit by the side that they're still looking to repeat. And you could certainly argue that the range here is not particularly great either, with just five values. Okay, on to the bit more of the analysis from the graphical point of view. So again, quite common to units be missing. This person's missed something off the time. We can also look at the graphs and we can see, well, have you got adequate repeats? What are your random uncertainties like? What's the uncertainty in the gradient? So if the error bars are right on this graph, we can see there's quite big error bars. They might not be right, but if they are right on the graph, there's quite big error bars for the larger values there. So should go back probably and have a look at that. We've also only got 5 points on the graph, and advanced tire, we're probably looking for more than that, 7. Often we're looking for 5 repeats. Often we're looking for 7, 8 different values, especially if it's quite a straightforward experiment. So it depends on how straightforward it is. If it's quite complicated, then we might do a little bit more about that. Really common with Excel that you can't see grid lines, so they're looking that the marker could work out the gradient from the grid lines on the printout. And therefore, if there are insufficient grid lines, this is a problem, even if you're reporting what the gradient happens to be. And this is quite tricky because sometimes with the colors that Excel prints by default, you can actually print them out and then they're not there, even though they're there on the screen. So it might be something that you want to bear in mind when you're getting students to print off their graphs and what they actually come out the printer looking like, because that's certainly a bit of a problem I've had in the past. If there are error bars, then there should be some description about where they're coming from. It's what, otherwise they're not really adding, and they are quite difficult to do because you would generally have to do a custom error bar, because most of the time the percentage uncertainty is going to be different for the different values, and that's quite hard to do. There's nothing in terms of when you how you support the students. You shouldn't do the graphs for them, but it's quite reasonable to show them how to do these things, either when you're doing experiments in class, or as more common as they're doing some of the work, you can show them how to do the things. I frequently do that, and then I either show them one and get them to do the other ones, or if there is only one, I'll show them how to do it and then delete it and get them to start it again and try it themselves, if you like. Okay, so then we have our linest that most people are starting to use. So that's in Google Sheets or in Excel to be able to get the value of the uncertainty in the gradient and the value and the uncertainty in the intercept. So here we've got more values. The 4 would be sufficient from there. And this is what's kind of called the box in the course reports in terms of reporting out. So it's quite nice to put that in as the values that are shown there next to the analysis part. I've put here, be careful with precision, because you can see how many significant figures are in there, and certainly a lot in the values at the bottom, like about 15 or 16. So, you know, a marker looking at this wouldn't condemn it necessarily just based on that, but if this is a common pattern, then that might sway how you think about things. So it's good practice to get them thinking about what precision they should need for the numbers, and of course pretty straightforward when they're using Excel or Google Sheets to change how many numbers are displayed in the cells. As always, very easy to make mistakes, particularly when converting. So correctly combine some uncertainties to get an uncertainty in L, and then incorrectly divided by 1,000 later on. And one of the causes a lot of issues sometimes in reports when you're not getting the values that you want is down to the units that are used, because some of the methods and some of the formulas that are in the older books are in different units, or a mixture of different units, so can cause problems. So if you are out by a particular factor, that's one of the things to focus on when they're looking at the value and thinking, oh, it should be 10 and it's 1,000 or 0.1. It's often a conversion thing somewhere. Okay, just like at National 5 and at higher, they should include their raw data, so not just the mean. So this person's put in the mean displacement, but everywhere in the report there was not any information on how that mean was calculated. How many repeats have they done? What have they got from that? Okay, it is possible if you're doing something on a data logger and there is lots of data, then that could be in an appendices, if there really were lots of repeats for particular things. So you can put it that way, but generally you'd be expecting to see it in what you have. Okay, also include other information that there. So sometimes they're measuring diameter of ball bearing for the viscosity one, or the dimensions of the capacitor plates. things like that, and sometimes they don't write them down. So they've got an area, but they haven't got the actual dimensions that they worked out to get the area. And of course, they would have uncertainties with those measurements too. So it's making sure that all those things that are measured are reported, and not just the things that they think are more important to report. Okay, like all physics, show working is a good idea. If you can show how you are calculating a particular value, it makes it much easier for the marker to look through and to see what you're doing and see where it's come from. They will be trying to do some of that themselves within the time that they're allocated to mark it. But if you show where it's come from, and it improves the readability a lot. Okay, just a little reminder in terms of what some of the terms mean. So if we are talking about accuracy when we're doing an analysis, we're talking about how close it is to the true or the accepted value. So how close a value for G would be to 9.8 meters per second squared, for example. If we're talking about precision, we're talking about how repeatable the measurement is the overall uncertainty low, and precision and accuracy aren't necessarily dependent on each other. Can be one without the other and the other without the other too. And then we talk about reliability. So not in terms of how the student puts it. You often see things like, yeah, it was a great experiment. I did really well. Well, sometimes you see that. But in terms of how small the random uncertainty happens to be. So here's the typical target slide. Are we accurate and precise? Are we hitting the bullseye and they're all in the same place? Are we precise? We're in the same place, but we're not accurate. Are we quite accurate, but we're not very precise because they've spread out? And are we neither? So this is quite a good thing to show students to try and do that. And it's also something that you want to do as you start to talk about when you're talking about experiments, to get them used to the language, because it is confusing for certain, and it's not necessarily always written down, some of these terms, particularly in sort of student-friendly or even teacher-friendly language sometimes. So moving on to the discussion and the evaluation sections. There is a mark in the report for the readability and how you structure it. So I'm really going to recommend that you just say to the students, right, there's that point, write something on that point. There's the next point, write something on the next point, which is what this candidate has attempted to do and done a pretty reasonable job of doing too. So it makes it much easier to mark, and it makes it much clearer to see what kind of things are you putting in. And of course, like experiments we do at other levels, you know, they can comment on things that they've done well to improve the accuracy and the precision of the results, not just things that didn't go so well or that they've got some problems, because sometimes that's an issue. You know, people deliberately try and do things badly, so they can say, "Ah, well, I could have done this." You know, if the room was darker, I would have been able to see the fringes better. And you're like, "Well, this is advanced high here, so we're expecting you to be in a pretty dark room in the first place." Really. So, you know, if there's some quite trivial improvements, we're really probably looking at that thinking, well, I think you should have probably gone back and had another go with if it's something that's along those kind of lines. Obviously, it will depend on how long the experiments take, because sometimes they do take a long time, and therefore, you know, it's not realistic to be repeating. But if it is, we're probably expecting them maybe to go back. It's the classic example. My student would be using a traveling microscope to measure something very precisely, and then not actually using the vernier scale on the traveling microscope, and therefore neglecting any of the benefit of using that particular method. And then me saying, well, you need to go back and actually use the right scale that I showed you and recommended to do for a particular reason. Okay, so it can help, because this person here has put some reasonable things in there, but they haven't put any headings. So I do think the headings are there. The markers are marking it all as a whole, but if it's clear and easy to see, and it also gives structure, then I would recommend that's the type of thing that is tried to be done, if you like. Okay, I see you've been answering some questions, Jenny, just bits and pieces, yeah. And right, so what else have we got here? Uncertainties. So a little bit about uncertainties. I've actually pinched some from one of your earlier presentations here, Jenny. So you are looking at advanced time, scale reading, random calibration uncertainties. You're looking for combinations. You're looking for sample calculations. It's great if your method has something to a power, because you can show that you understand when it's to a power, that you multiply the uncertainty by the power. Obviously, we can't all have that because not all things have got squared or cubed or square rooted terms in them. But if they do, that's really good, because you can go, somebody understands how this bit works. Got a definition about calibration uncertainties, because that is new to advanced hire. There's a link just coming up, which on Jenny's website for some sort of common ones. If you can't find things, then I would just make an estimate of it, sometimes the same as the scale reading uncertainty. Sometimes it's different to that, but if you make an estimation of it, at least the candidate showing that they're aware that they should consider these things within it. Because it's more about the being an awareness necessarily than what value they are. And sometimes if they're looking at sort of calibration uncertainties in terms of meters and things like that, they are quite complicated as well, because it's plus or minus a bit, and then it's a percentage in the reading and things like that. So there can be occasions where you might simplify that slightly, but just say there is it's an awareness that the market's kind of looking at. Your analysis is much easier if you've got percentages, because you can see which ones are significant. And then you can look at, is it a low random uncertainty, making it more reliable? Is it more accurate because it's a low scale reading uncertainty? All of those kind of things are things that you can consider. Tables can make it really clear to see. Often these are quite large when you've got each value, and then you've got the combinations, and then you've got more combinations as you do the calculations from there. But I would recommend that approach to be done in most cases, because it's much clearer to see what's significant and what isn't. You can also round them in terms of looking at your information in your table. Sometimes I have more significant figures than I might do just to show that they're really small, because Excel might show they're all 1%, but maybe I want to see that it's bigger for the first row than the last row. So I'll put in the next decimal place, so I can see one is 0.7 and one is 0.1, just so I can see there's a difference in the values. And there's a link to the documentation that was provided in one of the national qualification things on uncertainties there, that you can have a look, and some of that's got calibration uncertainties for general bits of equipment in there. In terms of systematic uncertainties, so be expecting candidates to comment on when graphs don't go through the origin, and to try and suggest reasons why that might be the case. And they might be commenting about the adequacy of the range of readings that they've got. So they've got 5 on this graph, so we might say, well, a spring with a mass on, they could have had more than 5, certainly. So that would be a kind of comment be making in terms of some experiments that we've got. And then probably the bit that's done the worst. The individual experiments and the evaluations are generally reasonable, but the overall evaluation tends to be a lot of repetition of the previous comments that are made. Now, it will be marked as a whole, so it doesn't matter where the evaluated comments are there, but there's a lot of statements that are repeated, so it's trying to avoid those kind of statements. An easy addition to most situations is, can you come up with some further work? So is there another experimental method that could be used to determine what you want to do? Chances are there probably is, or could you do something with your existing methods to improve it, to do things from there? So I think that's a really quite an easy one. And sometimes there's 3 for the overall evaluation marks, and sometimes if you're seeing that and a little bit else, you're thinking, well, that's 1 mark that I could give in that section, because you do see a lot of the equipment was really old, or the equipment worked really well, or the equipment didn't work very well, type of things. Yeah, and then it's avoiding things like the best result. Well, what do you mean? The most reliable result, the most accurate result, the most precise result was experiment 2. Those kind of things that are there. Okay, I haven't put much else in on there, I've just realized, but there we go. But we can take questions on that in a bit because we're moving towards the end parts. In terms of referencing, doesn't matter if it's Harvard or Vancouver notation. This person here hasn't got the references numbered, so that's no good. They're also missing some information in terms of what pages they might have got out of advanced physics, for example. So they need to follow clearly what they're doing. I think the Vancouver notation is easier. That's the one with the numbers, just because they just put the citation of the number at the relevant point and then look up the other bits. But Harvard's okay too. So this one's a bit better because they have put titles and they have put the URL and they have put the date visited and they have listed things out. It's not quite in the classic research paper order, if you like. They've listed out the various bits, but if it's clear, I think it should be okay from there. You're looking for 3 correctly cited and referenced, and the same publication will count as 1. So if it's Tyler page 20 and Tyler page 30 and Tyler page 40, it's only 1 reference. So they need to have more than just that, to make sure you've got things that are there. This person's got a bit of a mixture of both here, I'm going to say, in terms of their citation, in terms of a number and in terms of some words. So that's not the best either. This person here, the image is cited. So personally, I would have cited the image down here with my little number to how lasers work, because it implies up here to me that it's the whole passage that they're citing, and they shouldn't really be citing the whole lot. So often you can have a citation for different pictures. Does it have to be exact? It needs to follow the criteria that are in the instructions for candidates, Paul, is what I'm going to say to that. And we're looking for 3 cited correctly. So that's why I think the number is easier to cite in the text, and then they just have to have a number listed correctly at the end. Well, 3 of them need to be listed correctly. So if they have a few, then it helps. But yeah, there are automatic reference generators that can help, definitely, in terms of what to do. But use the guidance to try and come up with what to do. If they've got books, the page numbers is sometimes things that are there. Obviously, they can have more of that or a range of page numbers. Most of the time, they're websites and things, but it should be fairly straightforward for them to cite a URL address correctly with the date accessed and author and a date, or unknown and a title or something, because it is something that's been tightened up on to make sure that there's consistency in terms of the marking approach, in terms of what they've got. Okay, and then lastly, we've got appropriate title. what it's about, contents page with numbers. So if you've got a last minute student and they haven't done one of these, they could literally take a piece of paper, write out contents page, stick numbers on each page, and that would help them get an extra mark for their project. Might be one of those that's really short, so it might be one of the few marks they get sometimes. I would consider, in terms of writing it, how it's structured. Personally, I find them much easier if they're written up as sort of individual experiments with an aim, method, procedure, diagram, results, conclusion, etc., like that. I think that's easier than ones where you get 3 different methods and then you get 3 different things, because as a marker you're flicking between the pages to try and look at what's going on. Some of them work okay like that, but I think they generally work better in a more kind of separate process in terms of readability. Sometimes I find there's kind of you can put underlying physics in different places, so you could have overall underlying physics about your project, and then you might have specific underlying physics for that experiment that's then going to explain what measurements you're taking and what you're going to plot on your graph and what some of the underlying theory of that bit is. So that's quite a good way to do it. The course report suggests that you can get high marks with reports with many fewer words than the maximum allowed words. So they allow 10% more than the maximum allowable, which is that 4,500, because I think it's 2.5 to 4,000. Need to check that, but you can get that without doing quite as many. So sometimes they are just too much, mostly because you're getting a lot of repetition from there. You can show them how to use Word. You can show them how to put in equations and things like that to do. You can do it to put in headings, and then it'll do automatic table of contents and things like that as well. That are really useful skills if they're going to go on and write reports. Definitely. Okay, people will count the words. Yes, and it is a 3-mark penalty if it is over the word count. Personally, I've never counted the words, but people do put exceptions if it's too long. But you get the idea when you read them, because some of them are just waffly and have a lot of things. So, but they've declared the maximum allowable word count on them, and you've got another one with the maximum allowable. And they're a bit different, but it doesn't include equations, calculations, and things like that. So if it's just in a Word document, there will be more words allowed than Word counts as Word, because it counts all words in tables and things. So if they're really close, they can copy it and delete and take out the things that aren't counted, like the references and so forth. Okay, so that is a quick look through. Hopefully that is of interest and helpful to you. I appreciate some of it is telling you things that you may already know, and some of it, when you look at the reports, is reflective just because the student doesn't listen to the teacher sufficiently to get some of the things right as well. But if you have questions, if you like, type any in, and then we can have a little look through what we've already been discussing a little bit, and I'm happy to talk about anything you would like.